In this video, I'm going to show how to analyze dynamic single molecule FRET data using Mars. So first, what we need to do is pull up the Mars docs website, and I'm going to follow closely along to one of the examples that we've provided. So I'm just going to search for GitHub, Mars docs. Comes up at the top here. So here's the GitHub repository that actually builds the documentation website. And the link here that ends with github.io will actually load the website. And we're going to go under examples, and we provide several different examples for tracking, a few different examples for FRET, and one example for flow magnetic tweezers. So in terms of FRET, there are three different examples that we've provided. One is for what we've called static FRET. This is the situation where you have fixed different distances and you don't have dynamics in your sample. Then we also have two different dynamic FRET examples. Both of these are actually using the same sample data, which is a Holliday junction that transitions between two different conformations, ISO 2 and ISO 1, as you can see in the cartoon here. And it does this on a relatively fast time scale so that you can see dynamics in the FRET region. So you can monitor with single molecule FRET these dynamic changes in the Holliday junction. And we have two different examples based on these data. So one of the examples is using full ALEX analysis, so using both donor excitation and also acceptor excitation, and alternating these different excitations to provide the complete information for ALEX corrections. And that's the one that I'm going to take you through in this video. There's a second dynamic FRET example that assumes you don't have direct acceptor excitation information. And that you can find down here in the link at the bottom, second dynamic FRET example workflow. But for now, I'm just going to click on this image here. That's going to take us to the page for this dynamic single molecule FRET data set. So at the top here, there's a sort of flow chart of globally the different steps that we're going to go through during this video. And there'll be sort of a phase one where we work with the actual video file itself, and we run a collection of Mars commands that are directly installed when you install Mars into your local copy of Fiji. And this is the peak finder, transform ROIs, the molecule integrator, and the merge archives commands. And we'll run these several times through to build three different archives here. In the second phase, we'll use a series of Groovy scripts specifically designed for this example that we will use in an action bar, which is kind of a convenient way to organize these tools so we can quickly get access to them and run them. And these will actually operate on the molecule archives we've created from the primary raw video data and identify bleaching positions, correct for the beam profile, add some additional tags, and then finally do all of the ALEX corrections to calculate the fully corrected efficiency and stoichiometry, and also apply a two-state kinetic model to directly quantify the exchange kinetics of the Holliday junction that we're looking at. So there's a few things we need to set up before we can get started. So I've installed a fresh copy of Fiji that I've placed in my applications folder on my Mac here. And the second thing that we need to do is actually to download the Mars tutorials repository, because this has all the scripts for phase 2. It has an example archive of the complete analysis and some Jupyter notebooks for calculating the final FRET distributions, and also for validating and examining the output of our FRET analysis. So to get that, I'm gonna pull up a second tab here. I'm gonna search on GitHub for Mars tutorials, which comes up here at the top. Otherwise, you can search under our lab website, our lab GitHub, and you can find this repository. Okay, so here we're going to go under code and we're going to clone this repository. Let's see, so where am I here? I'm just in Mars. I'm going to put this into documents. So git clone, and then I'm using the address I just copied. So one important thing to note is that we use LFS, which is this large file storage version of Git. So it's really important that you have installed Git LFS and you've also installed that into your local account. Otherwise, when you download the Mars tutorials, the larger files, which are the YAMA files, those are the molecule archive files, those files might just be very small pointers instead of the actual complete files. Complete files are a couple hundred megabytes in size. So now it's finished. So I can just go into documents here and I now see Mars tutorials, which I can open up. And if I go under example workflows and FRET, you can see several different folders here for the different examples. The dynamic, which we will do in this video, no acceptor excitation, and the static. If I open up dynamic, here you can see the Holliday junction merged YAMA, which is 530 megabytes, and the associated rover file. The rover files store information such as the window size and the presets for how the window, the molecule archive window was opened or saved from Fiji. Then there's also two Jupyter notebooks, dynamic FRET example, which actually calculates the E and S distributions, and the dynamic FRET validation report that evaluates how we filtered the FRET data. Okay, so we have this here. Now, in terms of our Fiji here, so I downloaded and installed a fresh version of Fiji. Then I added the Mars update site, and I also added the update site for the action bar that we'll use. And then there's two other things we need to install to do this example. So in the Mars docs, or excuse me, in the Mars tutorials, there is a folder called plugins, and in there it says action bar, and this actually holds the action bar, which is it's a separate window that will open, and it has a bunch of really convenient buttons that organize the Mars commands and the scripts that we're going to run. And those instructions are in this FRET power tools txt, and then there's a macro here that will allow us to open this from the action bar menu. So I've copied this into plugins, which you can see here. Second step, under scripts, I've created a new folder called FRET, and I've copied all of the scripts from the example workflows FRET scripts folder here into that FRET subfolder of the scripts folder inside of my Fiji. So right here, I'm actually inside of Fiji-example, which is the one that I'm using for running this example. So the final thing that we need is the actual data that we're going to analyze, and that is available on Zenodo. So at the top of our page here, we can open in a new tab the link to Zenodo, and here we've included a bunch of separate positions from the same experiment. So each of these could be analyzed individually, as I'll show you in this video. So we have position 0 through 9. I'm only going to analyze position 0. So I went ahead and downloaded that, and also the beam profiles here, and I put those into my documents folder, which you can see here, position 0 and the beam profiles. All right, so back to the example. So now we have all the files that we need in place. I'm going to go ahead and open my Fiji. There's a few things that I like to check in Fiji right when we've started. So I already went under update, and I updated once, closed, opened again, and then I updated again after adding the Mars update site and also the action bar update site. We can see here a FRET menu, which has the scripts that we'll be using, which I installed in the scripts subfolder inside of the Fiji. And then under plugins under action bar, I can open up the FRET power tools, which will bring up this very nice window with a bunch of buttons to streamline the process and make it a little faster when we use these tools in sequence. So I'm just going to move these windows out of the way to reduce the clutter and avoid some confusion. And I'll keep this down here. So let's see. So a few other things that I like to check in my Fiji are that we're going to open this video using SciFIO. So the video was collected in Micromanager 2, and we've written a SciFIO plugin for Mars that nicely opens these types of videos. So I just want to make sure that SciFIO is turned on. For that, I go under Edit, Options, Image J2, and I check the box. So it is turned on for SciFIO. Second thing I like to check is the memory to make sure we have sufficient memory allocated for the example under memory and threads. So here 16 gigabytes is plenty. Any more than 10 should be more than enough. But if you have lower amounts of memory, it might be that some of the commands don't finish and Fiji slows down. So I think it's definitely a good idea to bump the memory up. All right, so now I'm going to go ahead and open the video. So I'm in my documents folder here, position 0. If I click any of these TIFF files and open, then this video from position 0 should open. So it's a relatively large video, so this takes a little while. I've also noticed when you repeatedly open these videos, it actually speeds up over time. All right, so here's our video. I'm going to go ahead and adjust the brightness and contrast. So this video has 2 channels in it, and each channel has 2 regions. Okay, so channel 0 is the direct acceptor excitation, and so here we see in the top region, which is the acceptor emission, a bunch of peaks where we've directly excited the acceptor dyes and we see their emission. There is a second channel, which is the one for FRET, where we've excited the donor. We see the donor emission on the bottom, and on the top we have the acceptor emission from FRET, where there was energy transfer and emission from the acceptor. And for every time point here we have both a channel 0, which is the direct excitation, and a channel 1, which is the donor excitation. Now, just as a note, in Mars we use channel indices 0 and 1, but this window here opened in Fiji is going to say C1 and 2. So that's a little bit confusing, but in our nomenclature we always use channel 0 and 1. We start with a 0 index. So let's look here. Now we have our video open. What do we need to do next? So we're going to start with phase 1. And so essentially what we're going to do is we're going to build 3 different molecule archives in sequence. One of them is going to be for FRET. So this is where we want to integrate molecules in the acceptor direct excitation channel and also in the FRET channel, both in the top and the bottom regions, and combine those. Then we're going to separately create archives for acceptor only. So these are molecules where the donor is not fluorescent, and they would only appear in channel 0 up here at the top when we've done direct acceptor excitation. The third archive we're going to build is called donor only. This is one where the acceptor has bleached, and so we only get donor emission. So those are peaks that are only visible in the bottom half of this video here, and you wouldn't have any transfer, and there's no peak at the top half in the FRET channel, which is channel 1. All right, so we've opened the video, and next thing that we like to do is we're going to basically use one frame to find all of the peaks using the peak finder, and those will be added to the ROI manager. And to avoid the potential that the first frame doesn't have one of the peaks as bright as other peaks, that these can of course fluctuate, what we like to do is to use the Z projection tool to take an average of the first 10 frames. And this reduces the noise, and it avoids that we miss some dimmer peaks that are dim in the first frame and then brighter in the subsequent frames. So you can see this for both channels. Next up, we're going to take this average image and select the region at the top in the acceptor excitation acceptor emission, and there we will actually detect the peaks and find the peak locations. So we'll do that using the peak finder, which is here. So here we're using an ROI from the image, that's the box, which we've defined at the top. Channel 0 is where we're starting. We're going to use the dog filter, and I'm using the settings that are also visible in the examples. Here I'm fitting with a radius of 3, so I'm doing sub-pixel localization to get a better fit of exactly where those peaks are. There's an integrate tab here in the peak finder. In this example, we're not going to use that integration mode. That would be an integration mode where you directly integrate the peaks that you see there, but in fact we want to integrate all of the different regions together and build one molecule archive. So this integration mode here would be useful for generating just a table of the integrated peaks from this frame. And for output, we're going to add these to the ROI manager, and we can also preview here which peaks will be found. So you can see that it's doing a good job of actually finding the peaks with these predefined settings. The first time you open this tool, it might have some default settings, so you have to enter all of these to match the example. Once you've run the tool once, it should save all the settings the next times, and you won't have to enter as many changes. So I'm going to go ahead and hit OK. Now I have my list of ROIs here. Now the next step is that I'd like to I have the positions in the acceptor emission region now, but I need the positions also in the donor emission, because in the end I want to integrate the fluorescence and the acceptor channel, the acceptor region, acceptor emission region, which is the red region at the top, and the donor emission region, which is the green region at the bottom. So the way that we'd like to keep track of that is when we talk about channel, we're talking about the excitation, whether it's donor excitation or acceptor. And then when we talk about region, that's the subregions of the camera, either acceptor emission, which is on the top, or donor emission, which is on the bottom. So here I've opened the Transform ROIs tool. This will actually take the ROIs in the ROI manager, and it will transform them from the top region to the bottom region. And here we have an affine 2D transformation matrix, which we established using a sample of tetraspec beads, where you get the same peaks in each region. And we also have a tutorial about that. We're not going to apply the inverse, because this particular set of affine coordinates is for going from the top to the bottom. Here are the co-localization settings. So first thing we can do is go ahead and preview. So you can see it's taking all the peaks we had at the top, and it's making a second collection of peaks at the bottom. If we don't co-localize, then we see that it's transforming all the peaks. If we co-localize, then we can actually check in the bottom region where we're transforming to, using a dog filter again, that there's actually a corresponding peak. So we're only going to get the FRET peaks where you have peaks at the top and the bottom, and we're going to filter the original ROIs we're transforming from, which is at the top. The output here is that we're transforming from the red region to the green region. And the names that we enter here in this output tab of Transform ROIs are going to then be really important, because they'll eventually define the column names that are in our molecule archive. So I'm going to hit OK, and now what you see is that each of these entries that we had now has a green and a red. So one of these UIDs, as we call them, has a green and a red for the top and the bottom. So now we have our ROI set and we're ready to do the integration. We'll use the molecule integrator to do that. it's already discovered that we have these red and green peaks. The boundaries here define the absolute boundaries for integration. So here they're just roughly defined as the top and the bottom of the image. This avoids issues where you can get artifacts by integrating over the boundary. Under integration, there's going to be an inner radius, which is the actual region right around the peak that we will integrate the fluorescence from, and an outer radius. This is the region outside, and we'll take the median background from this local region for each peak and subtract it to establish the background level. Now here there are two channels, so it's channel 0 and 1. These actually have labels on our video of 637 and 532. So 637 is the laser that was used, that's for acceptor excitation. 532 is for the donor excitation. And here we have menus to decide, do we want to integrate that channel? Do we integrate that channel for all regions, or do we want to integrate the channel for only one of the two regions that we've defined, the red and green? So here, when we directly excite the acceptor, we are not interested in the green region of the donor emission region because there's no fluorescence there. So for that, we'll use red. For 532, we want to integrate both regions because that's the actual FRET laser pulse. And finally, for the output, we use the microscope called DABI for this. The metadata UID will be random. That's what works best. And that's actually required for this example. This metadata UID, it's a unique identification number for the video and the data set, which goes in the metadata tab and is also associated with all the molecule records. And we'll keep verbose checked here. That adds some extra columns, such as the mean background correction and the uncorrected integrated fluorescence, in case we want to investigate those at a later time. So one thing when I run this molecule integrator, it's very important that I don't use the average image, but I actually use the original video with all of the frames. Otherwise, of course, I'll only be integrating a single time point, but in fact, I want to integrate all time points. So I'm going to go ahead and run this tool. All right, so what this has done is it took the ROIs that we had, and it took the instructions that I entered in the molecule integrator multi-view dialog, and it used those to integrate the positions for each channel for each region, and it combined all the information for each individual molecule into individual molecule records. So the first tab here we have is the dashboard, and there we can just look at the information. There's 522 molecules, one metadata record, because it was just one video we integrated, and we're storing in normal memory. In the metadata tab, it holds the information about the video. We have one entry there. Here we can actually see the OME specifications, so the different channels and time points. And under those, there are quite a lot of different pieces of information that were extracted from the video, including things such as DT. This is the raw timestamps from the frames, exposure time, and a lot of other microscope settings have been integrated there. So this first archive that we made was for FRET. So this actually has the information to correlate fluctuations due to transfer between acceptor emission and donor emission. And so I'm going to add a tag here called FRET. Now if I go to the molecules tab, you can see here a bunch of different entries for individual molecule records. There's no plot information yet, but in the table we have the T, which is the time points, the OME time points. That's the numbering of the frames starting at 0. We actually have the time in seconds. This is taken from the metadata in the video, so not all videos have this, but we have this here. We have the location that was integrated, and 637_red, that's the actual integrated fluorescence that's corrected. And in addition to that, we also have the same columns for 532 red, so that's the 532 channel in the red region, and then finally 532 green, which is the 532 channel in the green region. So there are essentially 3 integrated fluorescence columns, and then a bunch of different associated features of each of those, such as timestamps and mean background and things like that. So the other tabs in the molecule archive are just for documentation here if you want to add comments, and then a sort of global settings here where you can add tag shortcuts, and there's some big data viewer options. So I have tagged the metadata with FRET. I'm going to go ahead and save this. I'm going to save this in a documents folder in a new folder. Let's call this HJ Archives. All right, so now we're done with building the FRET archive for now. One thing I just realized is I just called it archive.yama, but in fact I would rather call it FRET archive.yama, and the rover file also needs to have the same name, and this rover settings file here then stores the record that we had open, the size of the window, where it was located, the dashboard settings, things like that. Okay, next step is to come back here. So we went ahead and we followed all the directions for the FRET archive from the example that I just showed you. Now the next step is that we need the acceptor only archive. And so here the difference is that we want to find only peaks that have an acceptor dye and that the donor dye is actually bleached. So one important thing here is when we start to make a new archive, we need to clear the ROI manager. And so here I'm just going to go ahead again, highlight the region that we're interested in at the top, run the peak finder. I'm going to keep the same settings. And again, I'm going to add the output to the ROI manager. And I can preview just to check. It looks good. So I'm going to go ahead and do OK for that. Sometimes it doesn't refresh until you use the scroll bar here. So now that I have those, I'm going to once again run the transform ROIs tool. And here I'm again going to be transforming the red region, which is at the top, to the green region, which is at the bottom. I can go ahead and preview that. So here this is transforming all the peaks that I found. And the point though is that that for this archive, I don't actually want peaks that are in red that match peaks that are in green. I actually want to co-localize, but I want to exclude any molecules that have a donor that is actually emitting photons, because here we only want the acceptor only molecules. So I'm going to activate co-localize. I'm going to use channel 1, the dog filter again, but I'm going to say remove co-localizing ROIs. And this is only going to leave the ones that don't actually co-localize, because these are the ones that only have an acceptor. And so I'm going to hit OK. And again, I have green and red entries for each of these UIDs for the location in the red region on the top and the green region on the bottom. And now to integrate this, again, I want to go back to the original video with all the different time points. I don't want the averaged video to be active. Go ahead and use the molecule integrator. It found these 48 red and green molecules. The boundaries are the same. The integration settings should be the same. So 637 red, 532 all. And so just the point is that we're using this acceptor only molecule archive we're building for applying some of the other corrections that we need. For example, when you excite with the donor excitation wavelength, do you also directly excite the acceptor, and by how much? And so we need specifically these molecules, and we also need to integrate all the positions for that. So I keep the same settings, and then the output I keep the same. So go ahead and do that. I get another molecule archive, again 48 molecules, one metadata record, And here I'm going to label this acceptor only. And then here I can see my different individual molecule entries. So I'm going to go ahead and save this acceptor only archive as AO in the same Holliday junction archives, and then close that, and again delete all of the entries in the ROI manager. And now it's time for the final archive, the donor only archive. So that's the third one here. So far we've made the FRET archive, the acceptor only archive. Now we want to make the donor only archive, after which we'll actually merge all of these into one, and at that point we'll be able to start phase 2 with the scripts. So here we're going to actually go into channel 1, the 532 channel, and select the peaks at the bottom. And we want to essentially find molecules where the donor is fluorescent, but the acceptor is not. So we're looking in the donor emission channel here. So I'm going to use the peak finder. All these settings should be fine. Go ahead and preview this. Finds quite a lot of peaks. And I'm just going to go ahead and add these to the ROI manager. Then I'm going to use the transform ROIs tool again. So now this is really important. Our affine 2D matrix was developed to transform from the top region to the bottom region. And for the donor only, we're actually going to transform from the bottom region to the top region. So here I'm going to apply the inverse transformation. Here we can just look initially at everything being transformed. So if I go ahead and preview, it transforms everything up to the top. Here it's really important in the output channel, so we're not actually transforming from region red to region green. We're transforming from region green to region red, because we're going from the bottom, which we've decided to call the green region, to the top, which we call the red region. So we're doing the reverse. So that's really important because this has to do with the naming that will be used for the columns for the integrated spot positions. Now under co-localize, we can hit activate. This is now looking to see where do you have a donor peak that actually co-localizes with an acceptor peak in channel 1. Of course, we don't want that. We actually want the ones that don't co-localize. So we're going to say remove co-localizing ROIs, which you can see here. So I'm going to go ahead and hit OK. And now we've added all of these to the ROI manager. And then finally, once again, we switch from our average image to the original video. I use the molecule integrator again. Same boundaries, same integration settings here. So for completeness, I just keep the same settings for all of the 3 archives, and those certainly work with the scripts. And then here's the output. So go ahead and hit OK. Now it's integrating this video at these locations. And now finally, I'm going to go ahead. So here's our archive. We have 285 molecules. We have 1 metadata entry as always. Now this is going to be labeled with donor only. And here are individual molecule entries. I'm going to go ahead and save this into the same folder. I'm going to call this, donor only. All right, so now we have finished building the 3 archives that we need, and now we need to merge these into one, so that we have all of these distinct subsets of molecules all in one archive for analysis and for calculation of all the corrections. So at this point, we don't need these 2 video files anymore, the average or the original one. I'll go ahead and clear the ROI manager. And then I'm going to come here to merge archives. And here you can see what the merge archives tool wants the directory. And the directory should contain all of the molecule archives that you plan to merge. And there won't be any graphical user interface or anything popping up. The archive windows won't pop up. It is all done in a headless way to maximize the memory management. So sort of archives are loaded and saved as you go, and so you don't have to load all the archives in at once into memory. So here, if I browse, I'm going to go to Documents. I'm going to go to Holliday Junction Archives, hit Open, and I'm going to go ahead and hit OK. Now, it's still running, and the way that you can tell if it's done is by opening up the console window. And here you can see that it started, and now it's done. And it says in total it merged 3 data sets, and that was it's combined 855 molecules. So now that that's done, I'm going to go ahead and close the RO manager, and I'll close this console for now. And I will now look inside of the Holliday Junction Archives folder. So in addition to the archives which I had saved, there's a new entry which is called merged YAMA, and that actually has the merged information from all the archives. It does not yet have a rover file because of course we haven't used it in Fiji or saved it from Fiji. That's when that rover file is created. So I'm going to go ahead and drag and drop that into Fiji. And then I have the final archive. If I go into Info, I can see there's 3 metadata records, which makes sense because I merged 3 archives, and all of the individual molecule entries. All right, so now if I check the metadata tab, it's very important that I had tagged the metadata based on what type of molecules I integrated, acceptor only, donor only, or FRET. And I see that I've done that, so now I'm ready to do the add molecule tags. This script will actually migrate from the metadata entries, these tags, onto the molecule records. And it's kind of convenient in the molecule records to be able to quickly filter by the type of molecule. And this is these tags are required for the later scripts in this pipeline. So I'll go ahead and do add molecule tags, the merged YAMA. And now if I go under molecules, I can see under tags I have all these different categories here. So I'm going to go ahead and save this. Okay, so the next thing I'm going to do is correct for the beam profile. And this is actually going to use 2 beam profile images for the acceptor channel and the donor channel. And it's going to use those to correct the actual intensity, the integrated intensity columns. So I need to open those 2 videos. So I had downloaded those from Zenodo. So if I go under Documents here, you can see beam profiles just here, and I have AEX for acceptor excitation and DEX for donor excitation. So I'll go ahead and open those. So what I've done here is I have followed the instructions in the example to actually make these, where take the sum of a bunch of images and take the median intensity, and I did that for both of these. And one important thing is that the profile correction script, it assumes that the maximum value is within the region that you're correcting. So that's definitely clear here for acceptor profile. For this microscope, there was actually a lot of background in the acceptor emission region on donor excitation, and so here I actually deleted that region, so it's set to 0 because only the bottom region will be used. So now that I have these 2 beam profile files open, I'm going to go ahead and do the profile correction. So here it's asking acceptor emission, acceptor excitation. That column is 637, that's for the channel, and the region is red. And donor emission, donor excitation, that's 532 green. Archive is merge.yama. Acceptor excitation profile is going to be AEX profile. Donor excitation profile is DEX profile. All right. So now that I ran that, I'm gonna get an additional column in my records, and that's going to be called 637 red profile corrected. So that's the acceptor emission integrated fluorescence that is corrected for differences in the beam profiles, and that will then be used in the subsequent scripts during the ALEX analysis. So that was step 2. Step 3 is to actually identify the bleaching positions in the traces. This is going to be done using the acceptor excitation, acceptor emission. So that's a nice channel to use to look for bleaching, and the donor excitation, donor emission. So I'm going to go ahead and run that. So again, it's the same column, 637 red, 532 green. And that is going to use the single change point finder to find the most likely position where bleach occurred. And those are then going to be added under the position tab over here. So we have the general info tab, parameter tab for calculated values based on the molecule, region tab, this is for highlighted regions in the plot, and then finally the positions tab, which will have, now you can see acceptor bleach, donor bleach, and it has these values in terms of the T, which is the time point index. Okay, but in the plot, we actually have not yet plotted anything, so let's go ahead and do that here. So we can click this little graph icon up in the corner, and that brings up the data options panel at the bottom. And here, if we go to our examples page, we can scroll down, and there are some suggested settings for visualizing our FRET traces provided. So those are down here. So I'm going to go ahead and add these in. So I'm going to add entries. So here we want to look at the time points for X versus 532 green. And the color that we want to use there is let's see, the color that we want to use there is going to be 0D47A, right? So let's over here, and go ahead and open that again. Custom color under hex, and I'm going to do 0D47A1. Right, now I'm going to add the second entry, which is T, and 532 red. And for that, I'll go ahead and do a custom color there too, just to entirely match the examples. 9E. And then finally, we have the red entry here. So this will be 637 red. So the first entry is the donor emission upon donor excitation. Second entry is acceptor emission upon donor excitation. So this is resulting from FRET. Third entry will be the acceptor emission on acceptor excitation. And here, the color is going to be B71C1C. All right, so now we have these three entries here, and I can go ahead and load some plots. The y-axis here I'm going to call intensity. You can see here. All right, just checking this audio setting. So here I'm just looking at the first FRET entry, and you can already nicely see that the acceptor bleach was nicely detected. Donor bleach was attempted to be detected. Perhaps here it's not the best trace, and it may not have been the best detection. So now you can actually go through the individual traces and actually evaluate these. And so the idea is, let's look at the general flow chart here at the top. So we finished phase 1, we're in phase 2, we ran scripts 1, 2, and 3, and then we're in the select molecules step here. So in this step, we actually need to add the accepted tag exactly as written here, capital A, accepted, to a bunch of donor only, acceptor only, and FRET molecules. And that's required. We have to tag some molecules as accepted. Those accepted molecules will be used in the Alex corrections script for calculating the efficiency, stoichiometry, and all the various corrections. So let's see here. So I can, if I click the plot here, then it will actually just show me the curve without the data options. It'll hide the data options menu, and so here I can look through. And so let's see my third entry here, for example. You can see the donor bleach was nicely detected, acceptor bleach was nicely detected. In red, this is the acceptor only channel, and acceptor excitation, acceptor emission. And then you can actually look in the FRET region here and see that you have this nice anti-correlation. So let's see, the blue here is the donor emission and the gray is the acceptor emission. So when donor emission goes down, acceptor emission goes up, and you have a lot of transfer. When the Holliday junction switches conformations, you have the anti-correlation and it switches. So acceptor goes all the way down, donor goes up. And here, these are the uncorrected intensities. So as we would run the ALEX script, we will add a bunch of different corrections that will account for the differences in the heights that you see here in the traces. All right, so I went ahead and I tagged a few FRET molecules and a donor-only and acceptor-only molecule. So to help with this process, you can go under the Settings tab and add a shortcut. And so I did Control-A equals accepted. So then as you would look through the different traces, you can very quickly tag them. So for example, at the top here, you can filter based on anything in these columns. Usually that's the tag. So if I filter for FRET, and I look here, if I want to tag one, I can do Control-A, and that'll add the accepted tag, or of course, I can also type it in. So I went through, looked through just and tagged a couple. To filter those, I can just, again, filter by accepted, and then I can easily look through and examine those traces. So I did the same thing for donor only. I tagged at least one molecule, or sorry, acceptor only, which you can see here. So here you only see the intensity from the acceptor, and then finally for donor only, the same. So here's one that's a donor only trace. So if you go into the dashboard, we have the info tab here. If you go the tags tab, you can also get the count of the different tabs. So there's a lot more molecules to look through, and I only tagged a few just so I could illustrate how this works, but definitely would take some time to carefully look through and evaluate the traces and decide which ones pass the criteria. So we outlined a few criteria in the example section there that you can look through, and I would suggest following those. So now that we have finished with the selection process, which is here, we can do the ALEX corrections script. So I'm going to go ahead and run that. So this ALEX corrections script, the archive wants to know the acceptor, excitation, acceptor emission. So here we're definitely going to use the profile corrected column, because that's the one where we corrected for the beam profile differences. So if you alter the pipeline, or the workflow, and you define the peaks different, or you manually correct the profile, then you could switch which column you're using there. But here we use this profile correction script, and so we'll use that column, and then we have the two FRET region emissions. So donor excitation, acceptor emission, donor excitation, and donor emission shown here. Now the gamma model is how we will actually determine the gamma correction factor. And here we have two options. So one is for static, and this is based around the static FRET example, in which there are two different kinds of molecule types. There's a short distance and long distance molecules, but there is actually no FRET dynamics within an individual molecule. So that assumes you have sort of individual molecules that have different FRET states, and using that static check radio button entry, will give you the right gamma model for that situation. Here we do have dynamics, so we for sure have dynamics between states in individual molecules and individual FRET traces. So we're going to go ahead and use dynamic molecules, and it's going to then use a threshold between the two states and then actually fit a line across the two different states, the high FRET and the low FRET states, to fit the gamma. And this was, at least in our work, what's given us the best values of gamma. So I'm going to go ahead and run that. So this does actually a lot of different things. It again corrects for background, and it recalculates efficiency and stoichiometry after sequentially going through all the different corrections, including the leakage, the alpha, and the let's see. So we have the alpha parameter and also the delta parameter, and as well as the beta and the gamma. And so now in the table we have a bunch of additional columns at the end. So representing here the further background corrected intensities. Then the IIE and IIS are the initial calculations for efficiency and stoichiometry. And then as we add additional I's here, we're adding more corrections. Then we also have FAD, FDD, and FAA, which is the fully corrected intensities. And then we also have two columns called sum, DEX, and sum signal. And those are actually useful for the validation notebook. So that's where we're summing the emission from the donor and the acceptor together, and that should be constant. Sum signal is the same, but also including all the signals, which includes the direct acceptor excitation, acceptor emission. All right, so that script ran, and it added all these columns. It also added a bunch of parameters, which we can see over here. Many of these are used for the validation notebook. So we've calculated coefficient of variation. This calculates the stability of the curve, and ENS for between the bleaches, the sum signal coefficient of variation, also the FRET Pearson's correlation coefficient. That FRET should be anti-correlated, so this gives us an indication of whether we have anti-correlation, which here is 0.8, so it's definitely strongly anti-correlated. So those are some metrics you can use when further filtering, and that will be used by the validation notebook. All right, so one other thing I just wanted to mention is, of course, if you notice that a bleach position is not correct, you can directly move these on the plot, and that will update the corresponding position over here. So as you go through the traces, you can also correct any mistakes that may have happened in bleach detection. So I'll go ahead and save this again. So now we've finished the Alex corrections, and we can go ahead and look at the kinetics using this two-state fit. So here the efficiency is ear, that's the fully corrected efficiency. For time, the time columns for each of these different peaks should be the same depending on how you did your collection. So here we're using 532 green time, and then this is going to apply a two-state model and give us a segments table where it sort of will show the fit of the two states based on a threshold here of just 0.4. So we go ahead and do that, and here you can see we have a new entry here that defines these transitions between the states. Now in order to see those, we would add a second plot on the bottom. So hit the plus button here to add a second plot. Click on that plot, and then I can pick time and excuse me, so it was 532 green time, and this for signal we'll do the fully corrected efficiency here, and of course on the top we have it versus t, not time. So if we want the axes to match, then we have to come here. So t is the actual sort of the OME based index starting at 0 of the frames, and the time in seconds is using the actual raw timestamps from the frames. So let's 5:32 green time, 5:32 green time, and okay. So now I'll go ahead and restart those. So now we won't see the bleach positions because those were calculated based on T, and now we're not plotting with T on the x-axis. However, we can now see that the transitions here are shown on the bottom for E. And when you first open, they won't be aligned. But if you rescale, you can then see these transitions. And if we go ahead and add the segments that we calculated here, then we can see just with a very rudimentary two-state model how it's fitting these state transitions, as you can see here. All right, so that basically takes us all the way through phase 2. One thing you can also do is check in the log, and in the log, if you go to the metadata tab, you have 3 different metadata records, and each one of them has a unique log. And this is so if you do some processing steps and then you merge, you have an intact log for each metadata record. You can basically look through and see all the tools and the settings that were used for this pipeline. Those are all saved in here. For the Alex script for the workflow for Alex corrections, you can also see the mean values for the different E value, for the different efficiency and stoichiometry, and the alpha, delta, beta, and gamma from this. This was just for the very limited set of traces. And we've included in the Mars tutorials a complete archive that is from 4 different positions in which we've gone through and added, accepted, or rejected data for all the molecules that were integrated. And you can directly load that in and actually examine those traces here. So I can see if I can go ahead and do that. So I'm in Documents again. I would go under Mars Tutorials, and we have Holliday junction merged gamma. Go ahead and open that. And it opened on my other screen. So here it is on this screen. So this has 3,500 molecules, and these are 12 metadata records. And here are a few that actually are seen in the figure in the manuscript. So here you can see some of the traces from the figure that were added. And if we just look at FRET accepted here, there are 600 accepted molecules that are then used in further analysis. So I think looking through these traces in this fully filtered data set would be helpful for getting some indication of how we chose to filter the data, and also to get a better feel for examining the different parameters, the correction or validation factors that are calculated. All right, I'll go ahead and save this again since we did the two-state model. So in this example, we used all the tools from PeakFinder down to two-state fit. So at the top are commands, the bottom are scripts. The other entries here are used in the no acceptor excitation dynamic, for example, where we do directly beam profile correction on the video, and we apply corrections without Alex, so without AEX. So basically that's when we don't have the acceptor emission information directly from direct excitation. So that's maybe a more common way that FRET data are collected, but Alex allows for better determination of the bleach and allows for better determination of a lot of the correction factors. So now that we're basically done in Fiji, of course, what we'd like to do is to go ahead and plot out our efficiency and stoichiometry distributions, and to also do some validation to look globally at the data set. A lot of this can be done in Mars directly using the dashboard here and also the comments, but it's a little bit more convenient to do this in Jupyter notebooks, and this a little bit more easier for most users that are very used to using Jupyter notebooks and working in Python. So we've provided some Jupyter notebooks that actually illustrate that. So I'm just going to go ahead and open those up. So I've installed Conda, mini Conda onto this account, and I've installed PyImageJ following the tutorial directions on the docs website. So you can see that here under tutorials, Python, how to open a molecular archive. At the top, there's some information about how to create your environment once you have Conda installed. So I have done that now. So now I would do Conda activate PyImageJ. So I called my environment PyImageJ, and I included in that environment Seaborn and Jupyter notebooks. And now I will go into the Mars tutorials, and I'll go into the example workflows, and under FRET and dynamic. And then here we can see there's two different notebooks, which you can also see here. So there's the example notebook and the validation notebook. And I'm going to go ahead and run Jupyter Notebook to bring those up. And I'll go ahead and click on the example notebook first. So I'm not going to rerun this right now. If you just directly use the Holliday junction merged YAMA that's included with Mars tutorials, you'll get the same entries that we see here. You need to provide, so you need to provide these two variables here. One is the path to your Fiji.app folder, and the other one is your path to the YAMA or the molecular archive you want to analyze. That would be the output of this complete FRET analysis where you run all the scripts. The Fiji you use, of course, has to have Mars installed for this to work properly. So here are just the general import statements, pulling in the data into an archive and YAMA file. And we define some utility functions to create a data frame from all the data and a couple other common functions. And here you can see scatter plots of S versus E as we go through the different corrections. At the very bottom, you can see the fully corrected stoichiometry versus FRET efficiency with these histograms projected onto each axis. And then also the fitting the kinetic parameters. So essentially looking at the exponentially distributed state lifetimes, the dwell times, and fitting those to get time constants. And then here at the bottom is just illustrating how we extracted some of the individual traces using Python to put those into the figure. Okay, the second notebook here is the validation report. Again, it's going to use the same exact YAMA file here, and this is going to use a lot of the parameters that were calculated, and this coefficient of variation and the Pearson's correlation coefficient. So again, we have the general setup. Then we actually build a large data frame where each row is a specific molecule entry and the parameters inside. And then we define a couple convenient plotting default settings. And then here you can see we've made histogram plots where we look at the accepted versus rejected traces. And here this is for the complete data set that's included with the Mars tutorials, where we have 600 molecules that we had accepted for FRET. You can see that the sum of donor acceptor signals has a relatively low coefficient of variation, meaning that it's constant. And a lot of the rejected traces were actually in this higher region where you might have real fluctuations. The signal is not constant, so this is a good indication of that. Here it's just split by video because we analyzed 4 positions. We also did the same for some signal, so this is the same thing, but also adding in the acceptor excitation, acceptor emission. And again, the accepted molecules have a lower coefficient of variation consistent with constant signal, and this really evaluates for if you might have blinking events or other photophysical events that are unexpected. We've also looked at state transitions that they exhibit donor acceptor anticorrelation, which you can see here in the Pearson's correlation coefficient, which they're nicely anticorrelated for the accepted molecules. And then here's just a few other evaluations of expected features in the data set. So this notebook is provided to look and evaluate the output of the analysis and the tagging in particular. And in this case, we didn't actually use these metrics to directly filter the data. We actually just filtered it directly ourselves by tagging. But if you want, you can use the smFRET Workflow 7 validation filter, Groovy script. And that's not included on the Power Tools menu here. That's in the FRET menu here under Workflow 7 validation filter. And that will actually allow you to decide on threshold values for filtering. So either you can tag valid molecules with accepted, so this would allow you to re-tag all your molecules. You can also remove the tag accepted from invalid molecules. So the idea is you would go through, you do some preliminary tagging, and then you could use your validation notebook to examine your data and decide on thresholds that are a good fit for your data. We expect that coefficient of variation and Pearson's coefficient should be relatively consistent between data sets, but we haven't explored these with a large number of data sets. All right, so that's a quick tour through how you can analyze dynamic single molecule FRET data, and all the information that I went through is also described in detail on the docs website. Just have to go back under examples, dynamic FRET. So step-by-step instructions without this video are there. And if you encounter any problems at all, you get stuck at any steps, we would love it if you would reach out to us on the scientific community image forum and under the tag Mars. So you can see, I think at the bottom here, there's also a link to the image forum where you can directly get to that tag. And right, so here if you go under install as well at the bottom, it says don't be a stranger. And you can click the ImageJ forum and it's the same thing. And if you have any problems, you can make a post on there or reach out to us either in the issues of some of the Mars repositories or in another way, and we'd be very happy to help try to troubleshoot what the problem was. And we're always looking for more feedback and tips on how to further improve Mars. Another final comment is just that this tutorial in particular was developed in a very modular fashion. And you can obviously appreciate now that there's a lot of individual steps, a lot of individual tools. These all could be combined into one, but we thought that it's more powerful to have them as separate individual steps because then they can be modified and changed depending on what kind of data you have, and it allows more flexibility. I think it also illustrates how Mars can work as a framework to build single molecule analysis workflows on. So thanks a lot for watching.